Welcome to another live session. I'm looking forward to answering your questions from comets to cosmology and everything in between.
So the first question is from Stan via email. What impact does the confirmation of gravity waves have on the theories of the ekpyrotic cosmology and string theory? How sensitive is it? Let's start with that one.
Sure. So the gravity wave detection is a profound affirmation of general relativity in what's called the strong field regime. All of the tests that general relativity has passed in its first 100 years, a substantial number of tests, such as gravitational lensing and so on, are considered weak gravity tests of general relativity because the gravity is weak compared to situations of a black hole or a neutron star. So the gravity wave detection is from black holes coalescing is a very direct detection of general relativity in a regime where it's never been tested. Now, as for connecting it to the ekpyrotic universe theory, and a little context is needed there, that's a theory that emerged out of theorists from Princeton and Cambridge some years ago, maybe a decade ago, which sort of finesses the idea of the Big Bang as a singularity, which has always been a logical problem for the Big Bang. In physics of any kind, infinities are frowned upon. That essentially means your theory isn't working. And so the ekpyrotic theory does not involve a singularity with the creation of the universe, and it provides a context for the Big Bang which involves higher dimensions of space. And a situation where other space-times could exist and other expanding universes or static universes could exist. And so it removes the Big Bang as the beginning of everything that could happen in space-time, because there's a larger context of multidimensional space-time where the Big Bang is just one event and our expanding universe is one space-time within the larger space-time. The gravity wave detection in and of itself does nothing to affirm or disprove that theory. That theory is going to be much harder to test because it really does relate to physics that happens under conditions that we can't simulate on the Earth with any accelerator. So testing the ekpyrotic theory, which really has not happened yet, is going to rely on something else. It's probably going to rely on signatures that we can get using very, very delicately and exquisitely sensitive measurements of the microwave background radiation, which is our diagnosis of physics in the very early universe.
Great. As a follow-up question, Stan would like to know how sensitive LIGO is and how small of a gravitational wave event can it detect? Does it take a black hole to impact to register?
So the first event detected in the interesting happenstance, it was days before the LIGO machine was supposed to start taking science data. It was still in at the very end of its test phase. That was a booming event. That wasn't a close call. It was 5 or 6 sigma. It was a very strong event because it was very massive black holes. And as you know, they were very far away, 1.3 billion light years away. So that gives an idea of the scope and sensitivity of LIGO, that if the black holes that are emerging are massive, at what we would think of as the most massive black holes that can result from stellar collapse, 25 to 30 times the mass of the sun, you have the sensitivity to see them, in this case, 1.3 billion light years away, and since they were easily detected, probably 2, maybe even 3 billion light years away. Now, of all the kind of signals that LIGO is likely to be able to detect, a black hole coalescence is the strongest signal. It's the most extreme disruption of space-time. LIGO will also see black holes coalescing and merging with neutron stars and neutron stars merging with each other. Because their gravity fields are weaker, neutron star relative to black hole, those events will be weaker. So at any given distance, the signal will be weaker. But clearly, LIGO has enormous grasp through the universe in terms of detecting events. Relative to the event that it detected, it can probably see through to about 1/3 or 40% of the age back to the Big Bang. So a substantial fraction of the volume of the universe, which is an extraordinarily sensitive instrument, really for the first one we have that can do this kind of science.
All right, the next question is from Sunil, who is on with us live. And Sunil asks, why is the speed of light a limitation? I have seen many scientific news stories where scientists are working on something faster than light, why is light speed the ultimate constant?
It's a limit and a constant. They're two separate issues because you can have a constant without being a limitation on something. It's a limit and a constant both out of theory and observation. Out of observation, the constancy of the speed of light regardless of the motion of the observer or the emitter or receiver of light or any other electromagnetic radiation, that emerged from the Michelson-Morley experiment, 1895, one of the most famous physics experiments of all time, because it was looking for the ether, this sort of intangible substance that might be presumed to pervade space through which light and radiation travel, and with respect to which light and radiation travel at 300,000 kilometers per second. And so they looked for the extra imprint of delta V, a little velocity plus or minus, due to the Earth's traveling in its orbit of the sun. And they couldn't find such effect. Regardless of which way the Earth is moving in its orbit of the sun, the arrival speed of light from a nearby star, is always the same number. So the constancy of the speed of light is an observational fact, and it's been found in many, many more situations than Michelson and Morley looked at. Einstein, recognizing the primacy of observation and recognizing that theories have to be guided by what we observe, he elevated the constancy of light to a foundational principle of relativity. So it's a fundamental principle of relativity. And he, of course, was echoing what James Clerk Maxwell did with the electromagnetic theory and the theory of electromagnetic waves, where the speed of the radiation, regardless of wavelength and frequency, is a single number. It's a constant, the speed of light. So there was plenty of theoretical basis for what Einstein did even before Einstein. By elevating the speed of light to a constant and essentially declaring that as a premise of the theory, you are led to the consequences that length or the size of something and time, or the rate at which time passes, are supple and are variables according to the speed of the observer. Also, mass is supple too, because as you try to accelerate something towards this limit, the speed of light, you end up rather than putting energy into its velocity and increasing its kinetic energy, you start putting energy into its mass by equals mc squared. And so its inertia increases, and you never are able to push anything, even a small subatomic particle, to the actual speed of light. Now, at the Large Hadron Collider, for example, enormous amounts of energy, a large city's worth of electric energy from the grid, is used to accelerate particles to within iota of the speed of light. The particles traveling in the LHC are moving at about 99.5 or 69% of the speed of light, but they can never reach it. All the energy you're putting into the particles does indeed increase their total energy, but it doesn't increase their speed beyond that magic number.
Right, the next question is from Ryan, who says, "Thank you for doing these, Chris. I understand the difference between Doppler shift and cosmological redshift, but I'm curious why photons get stretched passing through the medium of space instead of simply taking longer to reach us unaltered."
So the cosmological redshift, the Doppler shift is an almost intuitive concept, and we can understand it in terms of sound waves. So some source of waves is moving as it emits the wave, and it's sort of catching up with its own wavefronts, squashing them, and therefore reducing the wavelength or increasing the frequency. When it's moving away from the waves it emits, it's stretching out the distance between the troughs or the crests and increasing the wavelength or reducing the frequency. So that's intuitive, and it works the same way for light as it does for sound. Cosmological redshift is different. It's essentially stating that the basis for cosmic expansion is expanding space-time. So it's actually the matrix, if you want to imagine it that way, the grid, the invisible grid of space in 3 dimensions plus 1 of time, that's expanding. And so if you could mark off invisible space with a grid, like a cube where the vertices were just points marking out invisible space-time, that grid or that cube, that lattice, is actually expanding. The distance between any 2 points in the space-time is increasing with time. And the interesting thing about the cosmological redshift, when you plug in the physics, is that that's what happens to a wave passing through that space-time. if you actually just go back to simple quantum theory, which applies in this situation, and you find that the oscillatory behavior of electric and magnetic fields, which represents light and other electromagnetic radiation, those wavelengths are affected by the space-time substrate through which they propagate. And so their stretching, or the redshift, is an actual function of the space-time itself expanding, and doesn't have anything to do with or to say about the motion of that radiation, where it's headed, or, I mean, it's always going at the same speed, but where it's headed, basically. The other thing is that general relativity doesn't put a speed limit on the space-time expansion, so it could be faster than light speed, that distance the 2 points in space-time are separating, which means that signals do not always get from one part of the universe to every other part of the universe. They can be, parts of the universe can be isolated from each other, or in the jargon of cosmology, beyond the horizon, beyond their local horizon, because of very rapidly expanding space-time. So the general relativity rules applying to space-time are different than the rules applying to electromagnetic radiation, which are special relativity.
All right, so Adrian had a question that was actually, I think you just answered it, which is, what is the difference between Doppler redshift and cosmological redshift? So hopefully Adrian will be satisfied with that answer, but I just wanted to acknowledge that we have received that question.
It means it must have been a good question. 2 people answered.
Exactly, it was timely.
In the same session.
So the next question is from Sunil, who asks, we believe in logical reasoning that effect follows a cause. How can you explain our existence from this logic if the Big Bang happened? What caused it, and why was there a need for a Big Bang?
Right, so there are sort of 2 questions in there, and I'll unpack them. The question of our existence, by which I take it you mean, intelligent life forms that evolve nearly 14 billion years after the universe starts. Although there is indeed a cause and effect chain that led to our existence, and we do think there are natural causes, and that there's nothing supernatural that happened, and nothing that's beyond the scientific method, the connecting the dots of the causal chain has not yet been done. And the part of the chain that's missing, we know how the ingredients were created. We know where carbon, nitrogen, oxygen came from. We know how planets were created, including the one we live on and the solar system itself. We know where the energy to support life comes from. The part of the story where we believe there is a causal chain, but we haven't identified it, is how did those simple ingredients aggregate to form the first basic cell with genetic material that could propagate information. That's a simple 1-sentence summary of biology. That's the basis of life. And that it's been speculated how that might happen, but the information storage of even the simplest genetic entity is quite substantial. Just recently in science, people working on sort of artificial life, or people genetically engineering organisms, have come up with an amazing microbe that only has, I think, 336 genes, which is phenomenal. I mean, we have tens of thousands of genes. There are some worms that have millions of genes. So they've created this highly minimal toolkit of life involving, like I said, a few hundred genes. But that few hundred genes still represents millions of base pairs in the DNA chain. So there's still a lot of information coded there. And nobody has managed in the lab to take simple chemical ingredients such as existed on the early Earth and show how they can generate millions of base pair long replicating chain like DNA or RNA, its precursor. So in that sense, there's a big gap, but it's not a gap that leads scientists to suspect causal reasoning or cause and effect. It's just one where we don't have the information yet, and it may be very hard to get it. On the other part of the question about the causal chain involved in the Big Bang itself, we have a big problem because the current cosmological theory essentially draws a line beyond a certain point. So tracing the expanding universe back towards the Big Bang, we have to draw a line at the point where the 3 forces that we understand fairly well, the electromagnetic force and the weak and strong nuclear force, hypothetically merge into a superforce with gravity. That theory of unification of all 4 forces of nature, we do not have. We do not have a physics theory for that. So as we trace the chain of events in the universe back very close to the Big Bang, tiny fraction of a second, we do reach this limitation of our physical theories. That doesn't mean that the Big Bang didn't have a cause. It means we cannot discern it, and we will probably not ever be able to discern it until we have a theory that unites gravity with quantum effects. And as you know, many people are looking for such a theory.
All right, so Adrian actually added a clarification, and so we'll go back to the Doppler redshift. So the question was actually, how do you measure the difference between cosmological redshift and Doppler redshift? So how do you distinguish between cosmological redshift and Doppler redshift in a measurement? How do you know that the spectrum is redshifted by one or the other process?
And that's a very good question, because operationally, it could be hard to distinguish them, that they don't have a different signature in the spectrum themselves. Either effect is essentially expanding the redshift by a numerical factor, or sorry, expanding the wavelength by a numerical factor. And that could be caused, so let's just take a galaxy as an example. A distant galaxy or a fairly nearby galaxy, but not one in the very local universe. That galaxy will have a cosmological redshift where it's being carried away from the Milky Way by the expansion of the universe. And the amount of that redshift is determined in terms of the Hubble law. So the larger the distance, the larger the redshift of that galaxy. That linear relationship was what Hubble found in 1929. So we measure the spectrum of that galaxy, and the global spectrum of that galaxy is imprinted with a redshift due to the cosmic expansion. And we know that it's the cosmic expansion and the cosmological redshift because that particular galaxy fits on this very clear linear relationship seen by Hubble. And so if we compare that galaxy we're talking about to any other galaxy at the same distance, we will find the same redshift. And that tells us, yes, it's cosmological redshift, expansion of the universe. Now within that galaxy, stars are moving, the galaxy is rotating if it's a spiral like the Milky Way. And so if we now have a telescope that can not just look at the galaxy as one blob of light, but actually start to look at parts of the galaxy, we'll see the different parts of the galaxy are actually moving at different speeds. And so, and if it's a disk, say it's a disk on its edge, then parts of the disk will be moving towards us at up to maybe 200 kilometers per second, and parts of it will be moving away from us at up to 200 kilometers per second. So inspecting a galaxy in detail, we'll see a range of velocities with a total range of about 400 kilometers per second that represents Doppler shift of the galaxy rotating about its center. And that is superimposed or essentially added to the global redshift the whole galaxy has due to cosmic expansion. So it's a good question because both signatures are present in the same object, and you actually have to drill down and get a little more detail to see whether you're talking about cosmic global motion of a single object, a galaxy, or internal motions of parts of the galaxy relative to each other, which is a Doppler shift.
All right, so the next question comes from Tushar, who asks, who's on live with us now, and asks, what is inflation? And would like to understand it in very as simple terms as you can.
Right. It's the only inflation, the inflationary idea or paradigm is the only major embellishment or alteration of the standard hot Big Bang model. So the standard hot Big Bang model emerged in the 1940s, really with people like George Gamow and Georges Lemaitre, of course. And it was cemented by the observation of the microwave background radiation in 1964, Nobel Prize winning discovery. So that's the Big Bang, the basic expanding universe with a early, very hot, very dense phase. Inflation came along in 1980 and 1981. I mean, Alan Guth is perhaps the most famous for inventing inflation, but there's others. Andre Linde, Alan Guth is at MIT, Andre Linde is at Stanford, and Starobinsky is a Russian, and there were several very prominent Russian theorists that were right in on the ground floor of inflation. So there were, 4 or 5 theorists who came up with and developed the idea within a few years at the beginning of the 80s. What they were reacting to were problems with the Big Bang theory. One of the problems is that the universe, if you just extrapolate backwards, the universe early on was expanding incredibly fast. And if the different parts of the infant universe were moving away from each other faster than light, and they were much faster than light, like tens or hundreds of times the speed of light, then in simple thermal physics, or in just sort of freshman physics, there's no way those different parts of the universe should have the same temperature, because they cannot transfer energy from one part of the infant universe to another, so they could not equilibrate their temperature. And so the fact that the microwaves in one part of the sky and the opposite part of the sky are the same to within 1 part in 100,000, 0.001%, is a complete mystery in the standard Big Bang model. It would have to be just a fluke or a coincidence. So the standard Big Bang does not explain why the microwave radiation is so smooth and so uniform from one part of the sky to the other. The other thing it doesn't explain is why the universe is so flat. The spatial structure of the universe early on, when it was small and a huge amount of mass and energy was concentrated in a tiny volume, space-time was very curved, highly curved, as general relativity said that it must be. In fact, now space, as close as we can measure it, is flat. This wasn't a great measurement back in the 60s, but now with microwave satellites, it's an exquisite measurement. Space is flat to within 1%. So there is no space curvature, and yet early on space was highly curved. Once again, that implies a coincidence that's uncomfortable. It implies that somehow there was tuning in the early universe to end up to have started with a highly curved space-time and somehow end up with a flat space-time 13 billion years later. So those are the two major reasons people went beyond the Big Bang towards this idea of inflation, which is the smoothness and flatness of the universe. A third, slightly more technical reason is that in the early universe, when particles and underparticles are coming and going, and there are all sorts of, bizarre particles, the kind of things that are produced in accelerators, were being made all the time, it was expected that there would be a topological defects, which is ruptures in space-time manifesting in a sense as subatomic particles, or the other word physicists have for them is relics. So these are massive subatomic particles like monopoles, magnetic monopoles. They're a prediction out of most physics theories. These should have existed in the infant universe with all that energy there to create crazy particles. And then in our universe, we should see them because, they would have been diluted by expansion, but not that much. And so the absence of detection of what are called relics, these sort of weird particle relics from the early universe, also is a puzzle. And these puzzles are all related. And inflation solves all of them at once. So this is not the most compact answer, of course, because inflation is a big idea and it's a little subtle. But the concept is fairly simple. You hypothesize a very early and extremely rapid exponential expansion of space-time that before matter and antimatter annihilate and before the universe starts to cool and before any structures are created or stable atoms even exist, the universe is stretched out by inflation by a massive amount. It's essentially 38 e-foldings or factors of 2.5, which is a huge number of orders of magnitude. So the universe expands by factors of trillions upon trillions in this tiny fraction of a second after the Big Bang. And the net effect of that is to solve all three problems. It expands space-time so rapidly early on that these relics, these strange particle relics, are vanishingly rare, and so we wouldn't expect to see them in the lab or in the part of the universe we can inspect. Space-time is, of course, fantastically stretched out from the way it started at the Big Bang, and so naturally enough, it's flat, and billions of years later, we still measure it to be flat. And it's also smooth, because the patch of the universe that we live in and observe when we look at microwaves in different parts of the sky represents one patch that was expanded by inflation to bigger than the visible universe. And so we should not be surprised that the temperature is the same on opposite sides of the sky. Inflation did that. So inflation, of course, cannot get credit for explaining the things that it was designed to explain, so we have to be logically careful about this. But those were the reasons those were the problems with the standard Big Bang that led to inflation being hypothesized. Those are the mechanisms by which it explains them. And then the extra ingredient in all this is, why could you imagine that something like inflation could have or would have happened at all? And there we reach into the tool kit of physics and particle physics. And the hypothesis is that out of this separation between the weakest force, gravity, what now is the weakest force, and the other three forces of nature, which amounts to symmetry breaking in physics jargon, the inflationary field or the inflationary driver could have emerged. So that inflation is triggered in the theory, in the one that was worked out by Guth and Linda. Inflation is triggered by these grand unification scenarios involving the fundamental forces of nature. So that's the kind of basis for the theorizing that inflation cosmologists have used for the last 35 years. There are problems about inflation. There are problems with the initial inflation as proposed that have been solved by a lot of detailed work. And there are still problems with inflation. It's not a signed, sealed, and delivered theory. The tests of inflation are weak tests. They're not convincing or compelling at this point. The one that would have been convincing if it hadn't evaporated was the BICEP 2 result from last year, the polarization of the microwave background. And people are looking very hard for that same signature that proved to be a mistake, an instrumentation flaw, or rather an instrumentation signature last year. That the motivation for that experiment has not gone away. Probably 6 or 8 different experiments are now trying to measure that polarization, because that is a very characteristic signature of inflation that we can look for.
Right, the next question is from Will, who is again on with us live. Recently, a report came out that astronomers experienced the shockwave of a supernova in visible light. Can you talk about how it was detected?
Yeah, so a supernova is emitting it's a blast wave, so it's a supersonic, highly supersonic shock wave passing through the medium around the supernova. And the sort of kinetic blast wave, which will clear out the immediate vicinity of a galaxy. For instance, the sun and the solar neighborhood seems to be in what's called a superbubble, because millions of years ago, supernovae went off one after another or related in time and cleared out a lot of the gas in the solar neighborhood. So a supernova will create a bubble in the galaxy that it goes off in. And then, of course, the radiation from the peak of the supernova will travel out in a spherical wave. And since the supernova brightens to the level of an entire galaxy, that's an extremely bright signal. And even diluted by inverse square law and the expansion of space itself, because if it's a distant galaxy, it'll be redshifted or lowered in energy. That's a lot of energy. It's like 10 to the 58 ergs or 10 to the 59 ergs, if you know what an erg is. 10 to the 7 ergs per second is a watt, if you want to get a sense of the power. So this blast wave is detectable in the form of its radiation component, which peaks a little while after the supernova goes off and then has a very slow decline for several months afterwards. And that was a fairly nearby example of a supernova where this blast wave was detected, not really the blast wave itself, but the sort of electromagnetic pulse that comes out from the supernova. Because it was a fairly nearby event and a very strong supernova, supernovae have different intrinsic energies, this was one of the most powerful known, it was a pretty impressive signal detected at many telescopes worldwide.
All right, the next question is from Ryan, who is on with us live. With LIGO's famous success, do you think that eLISA is a sure thing now?
LIGO's success has legitimized gravity wave research, absolutely. So that's a profound result for that reason. It's taken this field that was esoteric, marginal, had really uphill battles getting funded. It was amazing that LIGO was funded, but it's been a struggle to fund anything else, and it's put it on the front burner. So eLISA, as the questioner asked, is a project, Laser Interferometric Space Antenna, that's the acronym LISA. It's a NASA idea from back in the 80s, actually, I think the late 80s, and the design studies done in the 90s, to do free-flying Michelson interferometer in space, typically using 3 different spacecraft. So formation flying spacecraft that are shining lasers between one to the other and creating a Michelson interferometer with long baseline of tens of kilometers. And so they're doing what LIGO does, only they're doing it in space. And the reason doing it in space is important is that LIGO is fundamentally limited at the low frequency end of what it can do by geological noise. Even though it's built, the two detectors are in the two geologically quietest parts of the United States, there's geological noise. So that actually kills the sensitivity of LIGO for low frequency events. The gravity waves from a compact object like a black hole, some cataclysmic event involving a compact object, they scale pretty much as mass goes, the frequency scales inversely. So the bigger the objects, either spinning or colliding or coalescing, the slower the gravity waves that result. So you saw LIGO with solar mass, with black holes that were tens of solar masses, have these pulse trains that involve changes of order seconds. So if you go up to millions of times solar mass black holes like we have in the center of our galaxy, the frequency of their gravity waves are millions of times longer than seconds. And so you're talking weeks or months. And the very biggest massive black holes in the center of quasars, there are years. And no ground-based detector could ever do that. You need the stability of a free-flying space environment immune from the Earth's situation. So that's the motivation for LISA. It's going to find a completely different regime of gravity waves resulting from large, massive compact objects, which we know exist in the universe. Every galaxy has a massive black hole, and it grew probably by mergers and accretion, so there's plenty going on. So eLISA, yes, has been very much given a big bump by LIGO's success. Now, it's not to say it's funded, because it's competing with some other pretty impressive missions. It's not just cosmology. It competes in a limited pie with planetary science, with all the fun things that we can do with exoplanets, with other types of high-energy astrophysics, with gamma rays and X-rays, satellites. All these missions have their own constituencies, and astronomers are excited about them. So it's not a given that eLISA will happen. It's also very expensive, several $1 billion. It's slightly unclear what the price tag is. But the truth is, LIGO's success is so dramatic that I suspect it'll happen. But we'll find a way to make it happen. It'll be international collaboration, I'm sure, because other countries are interested in gravity waves. The price tag is very high, and we know how to cooperate in these kind of big missions, as Hubble and JWST show.
All right, the next question is from Will. And even though you've talked about it a little bit, we can address this very more specifically. How can galaxies move away from each other at faster than the speed of light?
Well, it's not. It emerges from the cosmological theory. So the expanding universe model is framed in terms of general relativity. General relativity is basically a formalism for relating mass energy density, where those two are interconvertible by equals mc squared, with space-time curvature, where space and time are connected in formalism of general relativity. So that's what general relativity does. And in terms of the dynamics of the universe, as how it expands, there is nothing in general relativity that has a speed limit. It's not built into the theory anywhere. And as most theorists would say, if it's not built in, don't add it, right? You don't add unnecessary knobs and whistles, bells and whistles. So general relativity in an expanding or a contracting space-time context has no speed limit. And in the actual universe we live in, when we trace back the current rather sedate expansion towards the expansion rate earlier on, we indeed find that you only have to go about 6 billion light years back towards the Big Bang before any 2 points in space were moving away from each other faster than the speed of light. So that's just emerges very simply from the theory. Special relativity does have a speed limit, but general relativity is the more profound and more generally applicable theory to apply to space-times, and so it supersedes special relativity in a sense. And so it's not just not violating general relativity, it's a part of general relativity that space-time can do this superluminal, as we would say, expansion. And that implies that not all parts of the universe are in causal contact or can see each other, if you like. Now, if the universe were slowing down, as it did for a lot of its history, then eventually the light from distant regions would catch up. You know, the superluminal, the spaces are starting to move at less than the speed of light, and so that gives light signals the time to catch more distant regions. But in fact, as we know, dark energy is causing the universe to accelerate in the last 5 billion years. And so some regions that have never been in causal contact, i.e. parts of space-time we've never seen, we will never see because of accelerating expansion. You can have regions of space, this is a little bizarre, but you can pick a part of the expanding universe scenario where you have a galaxy that was beyond our view because early on it was moving away from us faster than light, that came into our view because dark matter slowed the expansion rate down, and that light reached us, and then in the distant future will go out of view again and go beyond our horizon because of the accelerating expansion. That's really weird, but that also is a standard part of the model.
Right. The next question is, what do you think about the hypertelescope being prototyped in the French Alps, which is a diluted telescope made from many small primaries in a natural valley landscape? Is there any future to this? Is this a potential alternative to the TMT?
Yeah, these are interesting concepts. So, you know, telescope building, the big telescope building projects, there's only a handful. And, you know, and people essentially have to do what they know how to do. So in the well-established world of big telescopes, the approach is just sort of bifurcated into two methods. The method used here in Arizona for our GMT telescope in Chile and for our LBT telescope on Mount Graham is to build the biggest single mirrors we can of high precision, which is 8.4 meters, and just put them together like flower petals, if you like to think of it that way, for the GMT. There's really a limit to how big you can make a single monolithic mirror. People think it may be 10 or 12 meters, and we're not planning to build anything bigger than 8.4. So that's one approach. And then the TMT approach, the approach used for the Keck telescopes, is to make much larger mosaics of hexagonal segments, each of which is a meter or so across, and laser align them to act as if they're one coherent, unified telescope. And by the time you take that up, you know, with the Keck telescopes, 36 of them, not a big deal. By the time you're talking about the TMT telescope, it's, I forget how many, hundreds, 400 maybe. That's a lot of work. Just the alignment of those individual segments is a phenomenal amount of work, and it's not clear how much you can scale that. So, to get to the question, you know, people have decided there are other possible approaches. You can mosaic telescopes such much smaller individual components that are really cheap to make, and maybe you end up saving money because our mirrors, our 8.4 meter mirrors, cost essentially $20 million to make each one. Well, maybe you can get that much collecting area with much simpler casting methods and much smaller subcomponents, and just have very, very large numbers of them. And maybe you sacrifice a little image quality in the end because you're really interested in a huge collecting area and detecting objects that are so faint current and even perspective telescopes can't reach them. So I think the world of telescope building is open to these ideas like the hypertelescope and others, liquid mercury mirrors, which the Canadians are using, and you know there are other ideas out there, because to go beyond the current generation of large telescope is probably going to take some experimentation.
All right, the next question is from, again, someone who is on with us live, and they would like to know, how is it that stars in a globular cluster, such as the Great Hercules Cluster M13, are so old that they predate the formation of the galaxy? What did they originally belong to?
So the age of globular clusters has had an important role in observational cosmology, because as the age of the universe became clear from the Big Bang model, essentially, you know, looking at the expansion rate locally nearby in the nearby universe, you can project back how long it was when all the galaxies were on top of each other. So that's the age of the universe in an expanding universe model. And then a much more direct measure of the age of the universe is what is the oldest age of stars you can find anywhere. And the oldest age of stars you can find anywhere through the early part of the 20th century was these globular clusters, these very old, tend to be low mass stars with very small amounts of heavy elements, which itself is a sign that they formed early in the history of the universe. And so measuring the age of globular clusters was a major research agenda through the middle part of the 20th century. It was a foundation stone of cosmology, essentially, a cross-check on the Big Bang model. But it also raises the question, how did our galaxy form? If you have objects like M13 with hardly any heavy elements and ages of stars that are getting close to the age of the universe measured by the Big Bang, then what's going on? How did the galaxy form? So the speculation is that because the globular clusters are the most extended stellar ingredient of the galaxy, and because they form not perfectly spherical, but a quasi-spherical distribution, whereas we live in the disk, which is a collapsed and smaller entity, that this is how the galaxy formed. The galaxy formed first in a spherical collapse and crystallizing or condensing by gravity out of this very diffuse and nearly spherical gas cloud. The globular clusters formed first. And because the gas cloud that formed the galaxy was not completely smooth, it wasn't just an overall smooth sphere, it had a lot of condensations and subcondensations on different scales, you could end up with a situation where thousands or tens of thousands or hundreds of thousands of stars all formed in orbits around each other at the same time. And they did it very early, in the very early collapse phase of the Milky Way. So they are the oldest stars in the galaxy. The disk would then form subsequently by collapse of gas and then conservation of angular momentum into a disk. And some people think the disk actually took a while to build up to its current size, actually maybe billions of years. And so naturally enough, the stars in the disk, even the oldest of them, are younger than the globular clusters. And because the disk is continuing to form stars, because gases continue to fall into the disk and make new stars, stars have been forming in the disk continuously. Whereas the halo of our galaxy, where the globular clusters sit, is like a fossil. It's like a relic, a sort of a frozen relic of the earliest collapse phase of the galaxy. And that's why those systems, the globulars, have the oldest ages we know of.
Right, the next question is from Ryan, who is on with us live. As I understand it, material going into a black hole falls ever more rapidly through time towards the future and reaches the horizon in the hypothetical extreme future. Is this accurate? And if so, how can it be said that there is an inside a black hole?
I'm not sure it's falling into the future. The reference, we can talk about it in two senses. We can talk about it in terms of the view from an external observer. So suppose, especially as a way of measuring the time aspect, because that's important, suppose as someone near the, not near the event horizon, just at a comfortable distance, we watch matter falling in. I mean, it could be a clock, so we're measuring time. Or it could be some radioactive particles, a smaller amount of matter, and the radioactive decay rate is the way of keeping time. If we do that experiment according to general relativity, we, with seeing no change in the timekeeping that we do, either by atoms or oscillations or body clock or whatever it is, would see the clock of the infalling material slow down. And it would slow down asymptotically as it reached the event horizon. Also, we would not see the transition past the event horizon. Essentially, the infalling object, whatever it is that we're watching, would have its clock slowed down asymptotically to 0, right? And the object would asymptotically approach the event horizon, but never cross it. And so we'd end up with essentially a frozen image, an eternally frozen image of the infalling object. That's what general relativity and black hole theory predict. You can see that it's only a hop, skip, and a jump from that notion to the holographic theory for black holes, where somehow information about the things that fall into a black hole are encoded into the event horizon itself. My sort of kind of pop science level description of that gives you a sense of where holography theory might apply. It's not tested. So that's what we would see. If we were now transposed to the infalling object, we can't be a particle, but imagine it's a small entity keeping time, then to the perception of the infalling observer, the time, nothing happens. I mean, they're experiencing very strong differential gravity as they fall towards the event horizon, and an acceleration, of course, of their speed. But their clock appears to be moving normally. And in the theory, they fall into the event horizon because it's not a physical barrier, it's just an information membrane, and they fall in towards the singularity, presumably. So there's no causality violation of time in either perspective. There's an extreme distortion of time from our perspective of the object that's approaching the event horizon.
All right, two people have very similar questions, so I'll ask both of those. So Amar and Chaitanya both would like to know how the newly discovered gravitational waves are important for the advancement of science, but then also what are their implications for astronomy?
For science itself, it's because we've never tested general relativity in this way. So it opens up a whole new regime of our gravity theory. It takes it from being just a theory, with wonderful, beautiful equations developed by Einstein and solved by him and by others. It takes it into the realm of experimental science. So that's a huge transition, and that's going to be a rich field for years to come. It's hard to detect gravity waves, and it's hard to build gravity wave detectors, but beyond the 2 LIGO machines and the one that's coming online in Europe, we're hearing about the Japanese, the Chinese, in Africa and Asia. There are other gravity wave detectors planned. So there's going to be a boom in this experimental science. So that's the impact on science. And that in itself, by observing more and more phenomena in the sense of strong gravity fields, is going to test general relativity. It's going to totally put general relativity to the test. So if it is not our ultimate theory of gravity, if it fails in some way, we will find out, because we're going to be really testing the theory in a new way. In terms of astronomy, so for science as a whole, it's a huge thing, testing our best theory of gravity, one of the best theories we have of nature at all. In astronomy, it's just going to open up all these possibilities of things that you might observe in gravity waves, including things that we didn't predict. It would be very surprising if LIGO doesn't detect signatures in gravity waves that we don't quite understand. The first detection was nice because, as most people saw in the media and the press releases, the signal that was observed with some degree of noise on it perfectly matched a simulation in a supercomputer of what the signal trace should be when black holes coalesce. So it was a brilliant matching of theory and observation. But we're going to probably see signals that haven't been predicted, and waveforms and traces and signatures that have people scratching their heads, and then that's going to be interesting. So I mean, everyone is highly anticipating what it'll be like when gravity waves are detected, not just like once in September and haven't heard anything since, but they're detected maybe every week or every few weeks.
All right, the next question is from Chaitanya. What does the discovery of gravitational waves hold for the gauge boson transmitting the force of gravity, the graviton? Mm-hmm. Do gravity waves imply anything about gravitons?
Well, yes and no. The gravity, the most important thing to test about the graviton really would be its transmission speed. It is an assumption of general relativity. It's built into the theory that gravity propagates, when a mass situation or a mass energy situation changes, that disturbance, the gravity wave, travels at the speed of light. And therefore, by implication, gravity as a force, even if nothing's changing and no black holes are colliding, it's just an object sitting in space, gravity itself is being transmitted, is operating at the speed of light. And that has really never been tested. It's very hard to test in the laboratory, though people have had some ingenious experiments in the last few years to try. I think those experiments have all been critiqued, and none of them are a slam dunk demonstration that a graviton exists and propagates through space at the speed of light. It's conceivable, it's quite possible that as we observe more gravity waves, we'll be able to see situations that allow us to deduce the signal travel speed of the gravity waves. And that would be wonderful, because that would be an affirmation that this sort of particle theory, gauge theory, as alluded to in the question, that underlies gravity operating as a particle, not just as a wave or as a force, is valid. And that, of course, is a hint of how we might reconcile gravity with quantum theory, where everything is particles and forces.
The next question is from Maria, who is on with us live. I know that the rotational period of the moon is exactly the same as the orbital period with no difference. Hypothetically speaking, if there was a difference, would we see the other phase? Maybe she means other side, after a long period of time.
Yes, we would. And so the moon, the jargon for this is the moon is tidally locked, and that's because the moon is a relatively large satellite relative to the size of the planet. It's unique in the solar system to have a satellite as large as the moon is relative to the Earth, as close to the Earth as the moon is to the Earth. And that situation essentially guarantees that the differential force of gravity acting between these two extended objects will just sort of grab that satellite and hold it with one face towards us. Mercury suffers the same situation relative to the sun. It's tidally locked to the sun, with one face always sweltering and the other face actually frigid because there's no atmosphere, so it's extremely cold. If the tidal force reduced for any reason, this grip that causes tidal locking would abate. And so, although we can't see that experiment, it is going to happen eventually, because due to interaction between and conservation of energy and angular momentum in the Earth-Moon system, the moon is moving away from us about 4 centimeters a year. It's been measured by magnetometers and reflectors left on the moon by the Apollo missions, so we know this. And if we play this out forward, and this is totally understood in terms of just simple gravity theory, the moon eventually is going to go far enough away from us that that tidal locking will abate, and the moon will start to exert rotation, and we'll start to see different faces of the moon and the dark side spinning into view and so on. That'll happen very slowly and gradually, but it's going to take hundreds of millions of years before it even starts happening. So this tidal locking is in place for quite a long time.
Right. The next question is from Rami, who asks, with the next giant leap to Mars knocking on our door, how can you see the human race as an Earth representative species, and how can we start a global space project?
Sure.
5 minutes.
So I think it's a challenge because Mars is such a stretch goal for humanity. It's so far, it's so expensive. The very simple calculations of human visits to Mars, and not even at the level of a fully self-sustaining colony, are of order $30 to $50 billion. That's just to visit, to have a successful visit and stay some weeks and do experiments and so on. A colony is going to be hundreds of billions of dollars. So the obstacle to becoming off Earth as a species or colonizing Mars is just the difficulty, the distance, the cost, and it's a hurdle to get over. However, if you get over that hurdle, then it starts to get easier. The big investment is to get a self-sustaining colony, even a modest-sized colony. It's a prerequisite of any such mission that the colony be self-sustaining. There's nobody thinking in terms of resupply ships, except in the very initial phase. There's nobody thinking in terms of long-term habitation that needs resupply from the Earth. That's what makes it so expensive and so hard. So this initial investment of a few $100 billion, a lot of money, over decades, is to get to that self-sustaining level. Thereafter, their technologies exist and we know how to do it. We can extract water from the Martian soil. We can extract oxygen from the soil to breathe or to combine with hydrogen to make rocket fuel. You can grow, whether maybe we're not growing potatoes the way the Martian did in the book and the movie, but we'll be able to have hydroponic farming, and those technologies all are understood, right? If you have water, if you have even if you have to create your own nutrients chemically, you can do that. So having a self-sustaining colony is not off the table, but it's not going to be a big operation, and you have this very big cost and time hurdle to get to that point. And like I said, it's hundreds of billions of dollars and several decades. So if you're willing to take the long view, the 50 to 100 year view, then yes, I do think that will happen. And having happened, we don't know how that will go, because the colony, having become self-sustaining, is essentially independent of the Earth if the people don't get homesick and insist they have to go back. And the colony can grow in a careful, planned way using the resources available locally, and we don't know what the limits on that would be. So that does, in fact, amount to an off-Earth, an offshoot of Earth civilization with a very modest beginning. And that would be an amazing thing to witness. And I think that's all we've got time for today. So it was a nice question to end with. I appreciate all your questions, very thoughtful, very probing, and covering a lot of ground. And we'll be back I'm off to Chile, actually, with the donors from the College of Science. It's not really a hardship, 10 days in Chile, traveling up from Santiago to the observatory, stopping in the wine country and doing poetry and wine for a few days, then into the high desert, Atacama. We'll be going to the Alma site up at 17,000 feet, and I'll be back on the 11th. I think our live session will be late that week. So until then, goodbye.